X18, simple and damped harmonic oscillations. Before we study simple and damped harmonic oscillations, we begin with the uniform circular motion. Uniform circular motion is a circular motion along a circle with a constant angular velocity. Angular velocity is defined by this one is uniform. So actual speed is measured using the arc length delta S, and there's a radius r, and delta S is r times angle of the sector, and delta S divided by delta T is the speed, and r times delta theta over delta T, that is r omega, that determines the speed, and the speed is uniform in a uniform circular motion. In addition, the angle of the sector increases proportional to time. It is proportional to time. Relative to the y axis, the angle is angle theta. With respect to x and y axis, it is omega t. Or if we choose another basis, that is n1 and n2, that has angle phase shifted by delta, then the angle measured from the n hat to this unit radial vector is omega t plus delta. In any case, it is a linear combination of two basis vectors relative to x and y axis. It has a x component, r cosine omega t, y component or r sine omega t. Relative to n1 hat and n2 hat, different basis vectors, because the angle measured from n1 hat is omega t plus delta. It is r cosine omega t plus delta, r sine omega t plus delta. We remember n1 e1 hat cross e2 hat equals e3 hat. In the same manner, n1 hat cross n2 hat equals, again, the same as e3 hat. That is perpendicular to the xy plane. As a result, we also have 2, 3 equals 1. And we have n2 cross e3 equals n1 hat. The same is true for this. As I already told you, angular frequency or angular velocity, it is one revolution is represented by the angle 2 pi, and this angle is dimensionless divided by period t. Theta equals omega t if we use E1 hat, E2 hat as a basis vectors. You have question, Choi Ji-hwan? Do you have question? And if we use N1 hat and N2 hat, omega t plus delta, and this delta phase is constant. So if I take the derivative, it is both omega. Number 2, unit radial vector. We know it is cosine theta E1 hat plus E2 hat sine theta. And if I substitute theta equals omega t, it is written in this form. Unit tangential vector is obtained by taking the derivative with respect to theta. And cosine becomes minus sine, and sine becomes cosine. Sure, if I take the time derivative, then ER hat dot is theta dot partial derivative ER hat with respect to theta by making use of chain rule. And this one is the same as this one, and we can replace this theta dot with omega. Therefore, ER dot equals omega E theta dot. This is ER, and circle is E theta. Its derivative is tangent, so it is parallel to E theta. Its derivative is tangent, but this direction is opposite to ER. This direction is opposite to ER. That's the reason why we have negative sign of it. If I take the double time derivative, then I need to take the derivative of this one more time. ER double dot can be obtained by omega E theta time derivative. And this time derivative written in here is I have additional minus omega, and the E theta is to be replaced with the ER. So if I take the double time derivative, I have minus omega squared and the same direction. The same is true for the E theta double dot. E theta double dot, if I take the time derivative ER dot, then I can copy this result. Substituting this result, I obtained exactly same style of equation. And this is the equation of motion for ER and E theta. Both the ER and E theta satisfy the same equation of motion. Exactly the same equation of motion. Even though the first order equations are different in sign, the second order equation of motion is exactly the same for both cases. And actually, this is called the simple harmonic oscillation, equation of motion for simple harmonic oscillation. The reason is that uniform circular motion's projection onto axis, either x-axis or y-axis, is a sinusoidal function. So now we make use of this result, and we can rewrite in terms of this. Remember ER equals E1 hat cosine theta and E2 hat sine theta, and E theta hat equals a minus E1 hat sine theta plus E2 hat cosine theta. So I can substitute these results into these two equations, and I can obtain the result for expressed in terms of the original Cartesian unit basis vectors. Then what I obtain is exactly the same style of equation. Here, I multiply CR to this equation and multiply C theta to this equation and add them up. Then what I obtain is the first terms is a double time derivative of CR ER C theta E theta plus omega squared, the same expression. And this one is actually double time derivative of x plus omega squared x equals 0. In the end, we obtain the equation of motion for every x that is constrained to move around the circle of radius r. And this equation, this two-dimensional vector equation, is called the simple harmonic oscillator, the equation of motion for a simple harmonic oscillator. And I can expand this one. ER is expanded in terms of E1 and E2. E theta is expressed in terms of E1 and E2. And I told you X1 and X2 are the Cartesian coordinates. So I can combine these two and these together to find the X1 and combine these two to find X2. And X1 and X2 are CR cosine minus C theta sine, and X2 is CR sine and C theta cosine. We have two constant coefficients. I can pull out the square root of this, and we find these two numbers. If I square these two numbers and add them up, then it is exactly 1. Therefore, I can parameterize this one as either cosine or sine. The simplest choice is this one to be cosine delta and this one to be sine delta. Then I can use the formula cosine cosine minus sine sine to add them up to find cosine omega t plus delta. In a similar manner, because we have exactly the same coefficients, it is again cosine delta and sine delta. We know how to add the cosine delta sine omega t and sine delta cosine omega t. That is the sine omega t plus delta. Therefore, even if we replace the representation from the polar coordinates to the Cartesian coordinates, the two coordinates have the similar structure. This omega t plus delta, we remember this delta the phase constant, this delta appears in this manner. In addition, we can add this x1 and x2 to real numbers by multiplying imaginary number, pure imaginary number, I, complex number, and add them up. Then we can find a complex number. This complex number satisfy the same equation of motion. Why? X1 satisfies this equation, X2 satisfies this equation, and I can multiply I all together, and this is a real number. Therefore, if I add them up, x1 plus I, x2, double time derivative, plus omega squared, x1 plus I, x2 equals still 0. Therefore, I can generalize this one to be extended to complex number. Complex variable is also okay. In that case, I can substitute this, or this. Any substitution satisfies the same equation of motion. As a result, the general solution of this simple harmonic oscillator can be expressed in terms of either this or this. Okay? By the false statement regarding the general solution of the following equation of motion. Cosine omega t, sine omega t, that's fine, because both of them satisfy the same equation of motion, alpha cosine omega t plus beta sine omega t. This can be a general solution. Arbitrary solution can be parameterized in this way, or by making use of the square root alpha plus beta squared and alpha square root alpha squared plus beta squared cosine omega t plus beta sine omega t style. I can add this one as either cosine omega t plus delta or sine omega t plus delta with some amplitude. So this expression is a general solution. This one is also a general solution. This one is also a general solution. And e to the I omega t, e to the minus I omega t, alpha plus beta, this kind of form is also a general solution. The detailed expressions are displayed in here. Okay, we have another way of finding the solution. The result will be the same, but let me expand this solution in powers of t. We know the uniform circular motion does not have any singularity. So x of t is a function that can be differentiable to all orders. There is no singularity, there is no discontinuity, so it is sinusoidal functions are differentiable to all orders. And we can, in that case, I can take the Taylor series expansion, and Taylor series expansion is nothing but the expansion in power series, t to the 0 constant term, t to the first order, second order, to the infinity, with some specific coefficients that determines the derivative at x equals 0. So, for example, if I substitute t equals 0, x of t should be a0, and x prime of 0, if I take the derivative, then a1, something like that. So an is the nth order derivative of x at t equals 0. If I substitute this trial solution that is a power series in T, then I can find the sum should satisfy 0. If I rearrange this summation into a single summation, I can combine these two in this form. This one shows that if this one is exactly 0, then every coefficient must vanish. Every coefficient must vanish. That means n plus 2 must satisfy minus omega squared multiplied by an. That is a geometric sequence. It flips the sign as n increases, and as n increases by 2, we have a double power of omega. If I substitute this result into original equation, I have two kinds of solutions. I mean, A0 determines A2 and A4, all even numbers, and A1 determines A3 and A5, all odd terms. So even terms and odd terms are completely decoupled, and summation can be made separately. And we know how to sum this one because this is a Taylor series expansion of a cosine, and this is a Taylor series expansion of sine. As a result, we end up with the same form, same kind of form, linear combination of cosine and sine that determines the complete solution for this simple harmonic oscillator equation of motion. That's another confirmation that our previous derivation of various kinds of parameterizations for the general solutions for the equation of motion for a simple harmonic oscillator. Now, let us once we determined how to parameterize the general solutions in these kind of forms, why don't we determine the exact solution that satisfies the initial conditions? Initial conditions are called the position at t equals 0 and velocity at t equals 0. As you know, we had two independent parameters that determines the initial conditions. Therefore, I can make use of this parameterization, and actually this one was x0 and this one was x dot zeros. X dot 0 is velocity and x0 is initial position. Therefore, let's substitute t equals 0 in here. Then x0 cosine 0 plus v0 omega sine 0. So that's right. And x dot 0, because x dot equals minus x0 omega sine omega t plus v0 omega. If I take this one derivative, it becomes a cosine omega t. So omega cancels. X dot 0 should be minus x0 omega sine 0 plus v0 cosine 0. That is v0. That's correct. So this one is an exact solution that satisfies the initial conditions. And that can be done by substituting these initial conditions into any one of these parameterizations for the general solutions. So, for example, why don't we choose this parameterization? If I substitute t equals 0, then I obtain x0, that is a cosine delta. Aha. And x dot equals a minus a omega sine omega t minus the delta. So if I substitute t equals 0, x dot 0 equals v0, and that is a minus a omega sine minus delta, and that is a omega sine delta. All right. We can make use of these results to determine the amplitude. And using these, we can determine the phase in this way. Find the false statement. This is the simple harmonic motion spring force in 2 dimensions. We assume that x is moving along the x-axis only. Then it becomes equation of motion is mx double dot equals minus kx. That is mx double dot plus kx equals 0. If I divide both sides with mass, we have mx double dot k over mx equals 0. We know spring constant is a positive and mass is a positive too. Therefore, positive number divided by positive number is positive number. This is a positive number. We call from now on, we use omega 0 to identify the angular frequency of the simple harmonic oscillator. Okay, so in that case, because we have defined this manner, the solution should be expressed in terms of the sine or cosine or exponential form with the argument omega 0t. And this omega is completely determined by this spring constant. So spring constant and mass. And again, period is 2 pi over omega, but we use omega 0, and we substitute this result at the inverse, the 2 pi square root m over k. We know mass is heavier, then period becomes longer, and the spring constant increases. It vibrates very fast, so period decreases. We have a simple harmonic motion of point mass with the trajectory. So omega 0 should be square root k over m. And delta is a phase constant. Using this relation, k equals m omega 0 squared is the spring constant. We remember this is F is a minus k E1x. Even the three-dimensional expression is okay. And if you compute the curl of this, then it is exactly 0. If curl is 0, using Stokes' theorem, curl F over a surface should be the same as a closed path that is the boundary of surface. And because curl is exactly 0, this integral is 0, and the closed path integral surrounding surface S, this is curve closed path C, is always 0. That is the definition of the conservative force. So total mechanical energy is always conserved if the curl of force is exactly 0. And in that case, there exists a potential energy that should be expressed as the force should be expressed as the minus gradient of the potential energy. That is correct. And you know how to compute the gradient of x squared, and this is x squared e1 e2 hat y component y squared and e3 plus plus and the z derivative z squared. Sure, the remaining pieces y z squared, this one can disappears and x squared z squared disappear because it is a partial y derivative, z derivative. As a result, this is 2 times e1x, e2y, and e3z. That is 2 times x vector. That is the reason why the potential energy is 1/2 kx vector squared. The kinetic energy of the system should be, let's return to the one-dimensional case for simplicity. One-dimensional case, it is x dot squared, and solution is substituted in here. We have m omega, this with the velocity, x dot of t equals minus a omega 0 sine omega 0 t plus delta. Therefore, if I substitute these results and replace this m omega 0 squared with k, the kinetic energy is 1/2 ka squared sine squared. And potential energy is 1/2 kx squared. Substituting this one, I have the same factor except that sine squared is replaced with cosine squared. Time average of both of them should be sine squared's average is 1/2. So we have 1/4 of ka squared. If I sum these two, it is 1/2 ka squared. That is the total mechanical energy. And even before we take the time average, we can add these two and apply sine squared theta plus cosine squared theta equals 1. Then the sum is again 1/2 ka squared. So time average is this one, and at any time, sum of the total mechanical energy is always conserved because it is a conservative force. Now we multiply x dot to this equation, and we remember how to reorganize this one as a sum of the kinetic energy and potential energy. And this is exactly equivalent form, and this one shows that time derivative of total mechanical energy, kinetic energy, and potential energy sum. This is time derivative is 0. That means this one is constant. Because this is a constant, let me write this one as mx dot squared plus 1/2 kx squared equals 1/2 ka squared, and multiply 2 over m everywhere. Then we find this expression. Now I have replaced this one is omega 0 is a square root k over m. And this one can be understood as the total mechanical energy that is invariant. In that case, that amplitude is completely determined by the total mechanical energy. And we find that a velocity squared is a positive definite, except that at the point where x becomes plus minus a, so x varies from minus a to a, it oscillates. If we consider the motion, this kind of oscillation, why don't we consider this motion? In this region, x dot is a positive. Backward, forward, backward, forward. So let us isolate this part only. And this, if I collect some of the time for this to translate from this position to that position, this is just one half of the period. Because when it returns, this whole time is a period. So this straight path from minus a to plus a determines the 1/2 of the period. Why don't we compute the 1/2 of the period? From minus a to plus a. I can make use of this one, x dot, positive case, omega 0 square root a squared minus x squared. Using this one, I can make use of 1/2 a period that is exactly the same as this one. 1/2 a period multiplied by omega 0. And omega 0 is here. Time can be measured by the displacement divided by velocity, because x dot equals dx over dt, and this value is exactly the same as dt. And x dot, this x dot, positive value, when I consider the motion from minus a to plus a, it is a positive. This one is substituted to cancel omega 0 in here, and I end up with this integral. I rescale this integral by replacing x with a that has the dimension of length and dimensionless number c that varies from -1 to +1. And this integral is a trivial integral called arcsine. And arcsine has the minimum value of -1/2 pi at -1, and this one has a value of 1/2 a pi. That's the reason why this value is minus 1/2 a pi minus 1/2 a pi, that returns pi. Therefore, if I use this one, 1/2 a pi, 1/2 a period is pi over omega 0, and multiply 2 pi over omega 0, I obtain the same result. Next, we consider the damped harmonic oscillator. Damped harmonic oscillator has additional force. If I rewrite this one, this is a force. Mass times acceleration is a force. It's minus bx dot minus kx. If I have this force only, restoring force only, I would have the simple harmonic oscillator. However, the additional piece is opposite to the motion. Velocity, but force is opposite to the motion. That is called the damping force. This is damping force, and B is a positive. Therefore, it is this damping force applies the force opposite to the velocity. That's the reason why if I multiply this force times the velocity dt, velocity dt, then this is dx, bx dot square dt. Time flows forward, positive, positive. It is a negative. And what is that? This is a F damping force multiplied by this one is dx. So force times displacement is the work. Work done by the damping force is always negative. That means the total mechanical energy decays. So total mechanical energy decays means this is not a conservative force. Equation of motion can be expressed in this form. I have divided the equation mx double dot plus bx dot plus kx equals 0 with the m. Okay, and this one is called b over m, and omega 0 squared is k over m. It is not negative, and if b equals 0, then gamma equals 0, and in that case it disappears, and we have a simple harmonic motion that preserves the total mechanical energy. Now let us solve the equation. First, why don't we try this trial solution? If I substitute this trial solution, what I get is derivative gives lambda, double derivative lambda squared, and the single derivative lambda, and then no derivative omega 0 squared, and exponential function equals 0. Exponential function can never be 0, so I can divide this one both sides. Then we end up with the quadratic equation that we call this a circular equation. And we call the value of this lambda to be eigenvalue or eigenfrequency. And the solution of this quadratic equation, the middle school students can solve this equation, and the solution is this. And this capital D is called the discriminant. And when the discriminant becomes 0, we have only a single solution that is a double root. If it is a positive, if D is positive, that means that this damping force is very strong, In that case, the frequency is two real numbers. Two real numbers means exponential something with real numbers does not oscillate anymore. So it is called damping force is very strong. So we call this case as an over-damped. And when this discriminant is negative, square root inside the square root is negative. Negative means it is I something. So exponential I something is always expressed in terms of cosine or sine. So sinusoidal solution appears only if we have this discriminant negative. When the discriminant is negative, the damping is not really strong. In that case, we call it underdamped case. And the case of double root, when this becomes the same to have vanishing discriminant, we call critically damped motion. So in three kinds of cases, we have mathematically the same kind of solution, but physically the style of the solution is absolutely different. For example, we considered underdamped motion that has a negative discriminant. When negative discriminant, we have omega 0 is greater than 1/2 of gamma. The imaginary part of the eigenvalue is this, because the square root 1/2 gamma squared minus omega 0 squared, this one is the discriminant and this is a negative. So it's better to pull out I, square root omega 0 minus 1/2 of gamma squared. And this is a positive real number. And I have I. And that I, because of plus minus sign, we have plus minus contributions. In every case, we have constant piece that has exponential minus 1/2 of gamma t is pulled out, and this exponential, imaginary part will brings in oscillatory term that is called cosine or sine. Now we have defined omega prime that is not the same as the omega 0 that is for the simple harmonic oscillator when gamma equals 0. When gamma equals 0, omega prime and omega 0 are the same. However, when gamma is not 0, omega prime is slightly smaller than the original omega 0 for the simple harmonic oscillator. This one shows the typical path of the underdamped motion. This exponential over factor lets the displacement, this exponential factor make the displacement shorter and shorter and shorter. And finally, it makes complete stop as the t goes to infinity. It makes a complete stop because of this one. And we have oscillatory factor that has omega prime as a frequency. Let it oscillate until it stops. The velocity has a similar kind of form, and we have two factors, and if I take the derivative, gamma-dependent derivative appears with cosine. And if I take the derivative of cosine, then we have omega prime style term appears. The sum of the potential energy and kinetic energy is not conserved anymore because of this damping factor, and it decays arbitrarily small. As t goes to infinity, the system loses all of the total mechanical energy due to the damping force. Again, omega prime is slightly smaller than the original omega 0, that is the square root of k over m. Next, we consider the overdamped motion. Overdamped motion is the case this discriminant is a positive. So if the discriminant is a positive, the eigenfrequency, eigenvalues are all real. So it does not have imaginary part. Therefore, there is no way to make an oscillation. So overdamped motion does not have oscillation. It just decays arbitrarily. And the strength of the oscillation, this decay, is a linear determined by these two pieces, and we have two different decay rate. And the linear combination of this is to make a general solution for this overdamped motion. We open the door, and sometimes to avoid slamming the door, we install the door damper. And door damper is a very nice example of overdamped motion. So overdamped case, we can see the displacement and velocity, both of them does not show any oscillatory motion, and its energy is strictly decreasing to make a complete stop. And again, I say, if the discriminant is a positive, eigenfrequency does not have imaginary part, and it does not oscillate. This is a special case. This is a critically damped motion. It used to be gamma, but gamma, 1/2 of gamma equals omega 0. That means gamma equals 2 omega 0. This is a special case that is called critically damped motion when this D discriminant is exactly 0. When the discriminant is exactly 0, the solution of the quadratic equation called the circular equation for lambda, it has double root. So it is a very convenient to rescale the solution as x of t equals e to the minus omega 0 t. Actually, it is e to the minus 1/2 of gamma t. But 1/2 of gamma is exactly the same as omega 0. So I substitute this result in the expression. Finally, if I substitute this one to find the first order derivative and second order derivative and substitute these into the original equation, what we find the equation of motion for this factor y is a very trivial equation, y double dot equals 0. And high school student can solve this equation by integration twice. That is, arbitrary constant plus arbitrary constant multiplied by linear function. As a result, the solution for the critically damped motion is this. It does have exponential decay factor, but we have only a single real frequency. And this is not related to the oscillation, but strict decay of the motion. Unlike the case of the overdamped motion that is strictly decaying, in case we have linear terms survive, in that case there is a single bump. It's not an oscillation, but we have exponential function that decays. We have function t that increases at small t. Because of this product function has the form like that. So this bump shows that this is a critically damped motion. However, it is not always true. In case C2 equals 0, again, it is strictly decreasing. So this kind of bump appears only if the critical damped motion has a term proportional to time. Okay, that's it for today.